We're going to start day 2 of neural control of exercising muscle by discussing action potentials. Now, as mentioned previously, action potentials are used in sending information to other cells through the release or lack of release of chemicals called neurotransmitters. And just like the last lecture, and actually really the previous couple of lectures, most of this should be reviewed, and a lot of these slides many of you will have seen before. However, after we get through action potentials, the next couple of lectures are not review, it's new information. So here is the topic and 2 outcomes for this lecture. Now, as discussed previously, resting potential is a steady state condition based on 4 things. Sodium influx, which by itself would make membrane potential less negative, and potassium efflux, the pump, and proteins, which make membrane potential more negative. Now, although membrane potential is constant, this would be considered steady state because sodium and potassium are constantly moving. Now, before we go to the stages of an action potential, it is important to remember that these 4 things are always working. In other words, sodium's constantly going through its leak channels, potassium's constantly going through its leak channels, the pump is taking these ions and putting them back, and then you've got the proteins that are hanging out there. Okay, so even when action potential is occurring, sodium and potassium are moving through these other channels. Now, an action potential consists of 3 stages: depolarization, repolarization, and hyperpolarization. But most of the time, a neuron is at resting potential. So with an action potential, we're going to add a couple of channels to our membrane. We have additional sodium channels. However, these sodium channels have gates on either end that are voltage gates. At resting potential, the activation gate is closed, but the inactivation gate is open. However, since one of these gates is closed, sodium is able to move through. And I want to reiterate for like the 7th time already, these are not leak channels. Leak channels are constantly open. These are voltage-gated channels that can open and close. There is also a voltage-gated potassium channel. This channel only has one gate, but this gate is closed at resting potential. And just to reiterate, this is different than the potassium leak channels. As mentioned before, resting potential is at negative 70 millivolts. Okay, and so we've got these 3 voltage gates that I'm talking about because these are the gates that will open and close that will determine when an action potential occurs and what stage of an action potential we are at. Now, in order for an action potential to occur, we need to reach threshold. And remember, threshold is just a specific membrane potential that must be reached to cause changes to these voltage-gated channels. In order to reach threshold, something happens that causes other ion channels to open. When these channels open, ions move in or out, which changes membrane potential. If in the case of a neuron, membrane potential reaches negative 55 millivolts, we will have reached threshold, and then an action potential occurs. And once an action potential occurs or starts, it's going to finish. Okay, something that we'll refer to later as the all or none principle. Now, when threshold is reached, 2 things happen. Sodium activation gates open, and they open quickly. Now, because the inactivation gates are already open, additional sodium can now move into the cell. Potassium, these voltage-gated potassium channels open, but they open slowly. So some potassium can leave the cell, but it happens at a slow rate because the gates are only partially opened. Now, due to the massive amounts of sodium entering the cell compared to the small amount of potassium leaving the cell, membrane potential becomes less negative, or in other words, it becomes depolarized. Now, the end of depolarization occurs at plus 30 millivolts when the sodium inactivation gates close. Now, although the activation gates remain open, sodium is unable to enter the cell through these voltage-gated channels because the sodium inactivation gates are closed. Remember, leak channels are always open, so sodium is constantly going in through those channels. Now, at the end of depolarization, or as the end of depolarization is reached, those voltage-gated potassium channels are still open, but they're not open all the way. In fact, they aren't fully open until the middle of repolarization. However, potassium is able to leave the cell throughout the entire repolarization phase. Okay, it just occurs at differing rates until that gate is all the way open. This causes membrane potential to return to its original negative state, or in other words, we're repolarizing the cell. This continues until membrane potential returns to negative 70. However, we aren't back to resting potential at that point. Instead, the neuron now experiences hyperpolarization. Hyperpolarization means to become more negative. The membrane potential becomes more negative because the gates reset. The sodium activation gates close quickly, the inactivation gates open quickly, but the potassium gates close, but they close slowly. And so during the first half of hyperpolarization, the slow closing allows potassium to continue to leave the cell through these voltage-gated channels. And these channels don't actually fully close until membrane potential gets down to negative 85 millivolts. Now that everything is reset, the neuron will get back to its steady state or resting potential of negative 70 millivolts. Resting potential goes from negative 85 millivolts to negative 70 millivolts, primarily due to potassium influx through the potassium leak channels. Although there is still much more potassium inside the cell than outside the cell, potassium comes back in, and this happens because of the electrochemical gradient. Remember those proteins that we talked about earlier? Well, they're negatively charged, and positive and negative like to be together. So even though there's a lot of potassium inside the cell, there's a lot of negatively charged proteins that help keep those potassium ions in the cell. Okay? And ultimately, we get back to our steady state of negative 70 once we get enough potassium back into the cell. And so now we've covered or reviewed the basics of an action potential. So are you able to answer the following questions? Identify the voltage-gated channels involved with an action potential, and describe what is occurring with each of these channels during each phase of an action potential.